Hello and welcome back to my YouTube channel. In this episode, we will dive into some exciting new features for our 2D platformer game. We will learn about creating a camera following system, enhancing our movement logic, and building a simple enemy system. In the previous video, we implemented basic character movement with collectibles and displayed the collected items on the screen. Currently, our character has a constant speed, and we use collider triggering to check if the character is grounded. While this works, it's not the most efficient method because it sometimes fails to detect jumps quickly, unlike in the original Red Ball game. To achieve this, we need to update our player movement script to include movement acceleration and more precise ground detection using raycasts. First, declare a new float variable named acceleration and set a default value. Also, declare a layer mask to identify the ground layer and a circle collider 2D to be used for raycast hit detection. In the start method, we will get the circle collider 2D component so that our script can reference it for raycast hit detection. We no longer need the onCollision enter 2D and onCollision exit 2D methods for ground detection, so we will remove them. Next, create a new method called groundCheck, where we will implement the new raycast hit ground detection. Inside this method, declare a vector2 variable to store the current position of the player and a float variable to store the radius of the circle collider. Now let's implement the raycast hit detection. In the groundCheck method, we use the physics2D raycast function. This function casts a ray from the player's position downward to check for collisions with objects in the specified ground layer. The raycast will extend slightly beyond the radius of the circle collider 2D to ensure accurate ground detection. If the raycast hits a collider in the ground layer, hit collider will not be null, and we set isGrounded to true. Otherwise, isGrounded is set to false. This method provides more precise and responsive ground detection compared to collision detection, especially for jumping mechanics where precision and speed are crucial. Now we will create a new method named move to implement enhanced movement logic with directional acceleration. This method will replace the current movement code in the update function. Here we're retrieving the horizontal input from the player. The input getAxis horizontal function returns a value between -1 and 1, depending on whether the player is pressing keys on a horizontal axis. We store this value in the moveX variable. This if statement checks if the absolute value of moveX is greater than 0.1. By doing this, we ignore very small inputs that could cause unwanted minor movements, which are often just noise from the input device. Inside the if statement, we set the player's velocity. The horizontal component is set to the product of moveX and move speed, while the vertical component remains unchanged. We also gradually increase move speed over time using acceleration multiplied by time.delta time for smooth acceleration. If the horizontal input is not significant, we enter the else block. Here, we reset the horizontal velocity to 0, stopping the player's horizontal movement. We also reset move speed to its default value of 5 float, so the player starts with the initial speed next time they press a movement key. This structure creates a responsive and dynamic movement system, ensuring smooth acceleration and deceleration, enhancing the gameplay feel. Now we will create a new method named jump to handle our character's jumping logic. This code checks if the jump button is pressed and the character is grounded, then sets the vertical velocity to jump force, allowing the character to jump while preserving horizontal movement. Now we will add the new methods for jumping, moving, and ground checking to the update function. This will ensure that these methods are called every frame, providing smooth and responsive character control. Let's test it in play mode to see how our improvements have enhanced the game. As you can see, the new ground check with raycast is working well, and both the jump and movement with acceleration are functioning smoothly, making our game look more similar to the original. Now we are going to create a camera following system. Create a new C# script and name it CameraFollow. Declare a public transform variable named player. This variable will reference the player's transform, allowing the camera to know the player's position at all times. Declare a public float variable named smoothSpeed and set its initial value to some default float value. This variable determines the speed at which the camera will smoothly follow the player. Lower values result in slower and smoother camera movement. Declare a public vector3 variable named offset. This variable specifies the distance between the camera and the player, allowing you to adjust the camera's position relative to the player. Declare a private vector3 variable named velocity and initialize it to vector3, 0. This variable will be used in the smooth damp method to keep track of the camera's velocity. Define the late update method. This method is called once per frame, but after all update methods have been processed. This ensures that the camera movement is updated after the player's movement, providing smooth camera following. Inside the late update method, calculate the desired position of the camera by adding the offset to the player's position. This ensures that the camera maintains a consistent distance from the player. Use the vector3 smooth damp method to smoothly interpolate between the current camera position and the desired position. The smooth damp method takes the current position, the target position, a reference to the velocity variable, and the smoothing speed. This creates a smooth transition effect for the camera movement. Set the camera's position to the smooth position calculated by smooth damp. This updates the camera's position each frame, creating a smooth following effect. Add the camera follow script to the camera object in the scene and assign the player reference. The offset z-axis usually needs to be set according to your requirements. In my case, I set x to 0, y to 2, and z to -10. Let's test the camera in play mode. Yay, it's working! Now, let's create an easy enemy patrolling system for this game. Add new layers named Player, Enemy, and Obstacle to manipulate these objects in the scripts effectively. Assign the player object to the player layer. Create obstacles to limit the enemy's movement. Assign it to the obstacle layer. Create obstacles to limit the enemy's movement. Create a new 2D sprite for the enemy and assign it to the enemy layer. Add a box 2D collider and a rigid body 2D. You can add a sprite texture to the enemy object. I found this one online for the tutorial, but you can also use primitive objects from Unity. Adjust the scale to a suitable size and configure the box 2D collider to fit the sprite. Create new scripts named Enemy and Player Health to handle the enemy's logic and the player's health. First, we'll add basic movement and patrol behavior. We'll make the enemy move left and right and change direction when it collides with an obstacle. Let's write the code and test it. Patrol speed defines how fast the enemy moves while patrolling. Direction is initially set to move left. In the update method, the enemy moves in the set direction. In on-collision enter 2D, the enemy changes direction when it hits an obstacle. Let's test it. Now we will implement health for the enemy and add the mechanics for chasing the player. The enemy will have its own health, and when the player jumps on the enemy's health will decrease. When the enemy's health reaches 0, it will be destroyed. Additionally, when the enemy touches the player from the sides, the player's health will decrease, and when the player's health reaches 0, the player will be destroyed. We will also add a force to the player's rigid body to create a bouncy effect during interactions between the player and the enemy. Chase speed determines the speed at which the enemy moves when in chasing mode. Detection range defines the distance within which the raycast scans for the player in the direction of the enemy's movement. The player layer is used to filter the player layer in the enemy script, ensuring that the enemy interacts correctly with the player. The transform player is used for the enemy to obtain the player's transform, allowing the enemy to track the player's position. In the start method, we need to find the player object in the scene. With a raycast hit while the enemy is moving, we search for the player layer by casting a ray from the enemy's position in the direction of movement, with the length of the detection range targeting the player layer. Now we extend the enemy's movement so that if the raycast detects the player, the enemy switches to chase mode speed. If the raycast does not detect the player, the enemy continues normal patrolling. Now we will extend the script so that the enemy has its own health and interacts with the player's health, which we will also develop. Now we will declare the following variables: an integer value for the health of the enemy, a bounce force for the bouncing effect when the player jumps on the enemy, a push force that will be used for interaction when the enemy injures the player, a layer mask for obstacles to filter obstacle objects in the enemy script, delay before slow for the patrol slowdown mode when the enemy's raycast loses the player, A scale-up factor for the animation of the enemy object when interacting with the player. Scale duration, the time needed to complete this animation. We will also use facing right and rotations to trigger the rotation of the enemy objects during its patrol, just like in the original game. Now let's define the update rotation method to handle the enemy's rotation during patrol and chasing. Initialize rotation logic. We'll check the direction of the enemy's movement and adjust the rotation accordingly. This will ensure the enemy rotates correctly based on its movement direction. Check if the enemy is facing right. If the direction is positive, right, and the enemy is not already facing right, we need to rotate the enemy. We'll increase the rotation angle, rotations, by 90 degrees and update the enemy's rotation. Set facing right to true to indicate the enemy is now facing right. In the else if block, we do the same, only now it's for the opposite direction. We call update rotation in the start method to ensure that the enemy's rotation is set correctly based on its initial direction as soon as the game begins. We declare a new float variable speed that changes its value depending on whether the enemy is chasing the player or patrolling. If the enemy is chasing, speed is set to chase speed, otherwise it's set to patrol speed. By calling update rotation in the update method, we ensure that the enemy's rotation is updated every frame, keeping it aligned with the direction it is moving. This makes the movement and rotation of the enemy look smooth. The fixed update method is called at fixed intervals and is ideal for physics-related updates. By handling the rotation in fixed update, we ensure that the enemy's rotation is updated consistently with the physics engine, avoiding any jittery or inconsistent behavior that could occur if we updated the rotation in the regular update method. We start by declaring a float variable rotation speed to control the speed of the enemy's rotation. We check if the enemy is currently moving with rigid body velocity not equals 0. This ensures that we only update the rotation when the enemy is in motion. We adjust the rotation angle rotation z based on the enemy's movement direction and the defined rotation speed. The angle is decreased or increased based on the direction of movement. We apply the updated rotation angle to the enemy's transform using Quaternion Euler. This smoothly rotates the enemy according to its movement direction. Now we will add logic to handle interactions between the enemy and the player in the onCollisionInter2D method. This will include detecting where the player makes contact with the enemy and applying different effects based on the contact points. We check if the object colliding with the enemy has the tag player. We get the contact point of the collision and the center of the collider. We determine if the player hit the top of the enemy by checking if the contact point is above the enemy's position and within the horizontal bounds of the enemy. If the player hits the top of the enemy, we decrease the enemy's health. If the enemy's health reaches 0, we destroy the enemy object with a 0.5 second delay to allow time for an animation. We apply an upward force to the player's rigid body to create a bounce effect. In the else block, we call the code to apply damage to the player. Now we need to create the methods in the player health script, which we made before, for this feature. We declare two integer variables, max health, which is representing maximum health the player can have, and current health, which will track the player's current health during gameplay. Next, we have the start method. This method is called when the script instance is being loaded. Here, we initialize current health to the value of max health. The take damage method reduces the player's health by a specified amount. If the current health drops to 0 or below, the die method is called to handle the player's death. The die method logs a message to the console indicating the player has died, and then deactivates the player's game object. We calculate a push direction based on the enemy's movement direction and apply a push force to the player, making the player move away from the enemy. We call the change direction method to make the enemy change its movement direction after hitting the player. Since we do not have this method created yet, let's create it now. First, we reverse the enemy's current direction by negating the direction vector. After changing the direction, we call the update rotation method to adjust the enemy's rotation accordingly. This ensures that the enemy's visual representation aligns with its new movement direction. An IEnumerator in Unity is used for creating coroutines, which are methods that can pause execution and return control to Unity, but then continue where they left off on the following frame. This allows us to perform actions over multiple frames, creating smooth transitions or animations without freezing the game. We start by storing the original scale of the enemy in original scale. Then we calculate the target scale by multiplying the original scale by scale-up factor. Next, we initialize elapsed time to 0 to keep track of the time elapsed during the scaling effect. We enter a while loop that runs as long as elapsed time is less than scale duration. Inside the loop, we use vector3lerp to interpolate between original scale and target scale based on the elapsed time, and yield control to Unity for the next frame. After the loop, we set the scale to the target scale to ensure it reaches the intended size. Next, we reset elapsed time to 0 to prepare for the scaling down effect, which works the same as scaling up, just in the opposite direction. To run the coroutine, we use the startCoroutine method, which initiates the coroutine and allows it to perform its actions over multiple frames. In our case, we will call this coroutine after the player damages the enemy, creating a visual scaling effect when the enemy is hit. Now let's create a new script called Health Bar to represent the player's health on the UI. This script will manage the health bar's slider component, allowing us to update the health bar as the player's health changes. We declare a public variable slider of type slider. This will reference the slider component in our Unity UI. The setMaxHealth method takes an integer parameter health. It sets the slider's maximum value to the player's maximum health and initializes the slider's current value to the same. This ensures the health bar is set up correctly when the game starts or when the player's health changes significantly. The setHealth method takes an integer parameter health. It updates the slider's current value to match the player's current health. This method will be called whenever the player's health changes, ensuring the health bar displays the correct value. Now, let's integrate the health bar into our player health script. This will allow us to visually represent the player's health on the UI. We start by declaring a public variable health bar to connect the health bar UI element with our player health script. In the start method, we check if the health bar is not null. If it's not null, we set the maximum health of the health bar using the setMaxHealth method. In the update method, we check if health bar is not null. If it isn't, we continuously update the health bar's value to reflect the player's current health. This ensures the health bar is always accurate. Now let's create a slider on the UI, assign it to the health bar script, and assign the health bar script to the player health. Now let's test it in play mode. Let's extend our player health script to include face expressions on the ball when we hit the enemy or the enemy hits us. We'll add variables for hurted sprite, normal sprite, and happy sprite to manage these expressions. The Change Sprite coroutine changes the player's sprite to a specified sprite for a given duration and then changes it back to the original sprite. This coroutine is used to handle the visual feedback for the player's interactions. We've created the Apply Damage Effect method to allow other scripts to change the player's facial expression when the player is hit by something. This method starts a coroutine to temporarily change the player's sprite. Since coroutines cannot be called directly from another script, this method provides an intermediary function. I have tested in play mode, and this isn't working because I mistakenly referenced a UI image instead of the player's sprite renderer. We need to replace the UI image with the correct sprite renderer reference for it to work properly.
Thank you for watching this tutorial. In the next video, we'll dive into some exciting new content. We'll cover basic sound effects integration in Unity, adding particle systems for in-game effects, creating enemy expressions, and adding physics objects like moving ramps and bridges with physics. We'll also build a main menu and a pause menu. Stay tuned and see you in the next video.